Imagine a robot navigating complex environments on its own. That's essentially what an autonomous car is. But how does it all work? Let's dive in to understand the 6 pillars that form the architecture of autonomous driving. First, infrastructure, the foundation of it all. Think high-definition maps, connected traffic signals, and communication networks that provide essential data for navigation and decision-making. Think of it as the map and traffic lights of the city, providing information about the robot's surroundings, that is, walls, obstacles, etc. Next, perception, the car's eyes and ears. Cameras, LiDAR, radar, and other sensors gather information about the environment, creating a real-time picture of the world around it. Third is sensing. Processing the raw data from sensors isn't enough. This stage extracts meaningful information, like the distance to an object or the type of road surface, allowing the car to understand its surroundings. Next, estimation. Where am I? Where am I going? This stage uses sensor data and the map to determine the car's location and predict its future position, which is essential for accurate navigation. Like a detective putting clues together, this takes the sensory data and figures out where the robot is and what's around it. Planning and control. Think of it like the brain of the operation. This stage analyzes information from previous stages, considers traffic rules and goals, and generates a safe and efficient path for the car to follow. Last, the actual robot platform, the muscles that put the plan into action. Steering, braking, and acceleration are controlled by this system, translating the planned path into actual movement in the case of autonomous cars. Let's further simplify to understand these pillars better. Imagine a complex dance, one where the car glides effortlessly through traffic, reacting to its surroundings as smoothly as a seasoned ballroom champion. This autonomous tango requires seamless collaboration between different parts, each playing a crucial role. Infrastructure and sensing. Picture them as the stage and music. High-definition maps provide the backdrop, while sensors act like instruments, gathering information about the environment, road lanes, pedestrians, buildings, and more. The map and sensors provide information about the surroundings, like road lanes, pedestrians, and buildings. Estimation. Think of it as the mini-map in the car's head. It takes the sensory data and figures out its own location, creating a real-time understanding of where it is and what's around it. The robot figures out its own location and the positions of things around it, like a mini-map in its head. Planning and control. Now comes the choreography. Based on the map and current situation, like traffic and speed limits, this stage decides the best route, considering safety and efficiency. It then translates these decisions into instructions for the dancer. In other words, based on the map and its current situation, the robot decides the best route, considering speed, safety, and traffic rules. It then sends instructions to the wheels and motors. Robot platform. This is the dancer, translating the plan into action. Steering, braking, and acceleration respond to instructions, adjusting for bumps and unexpected situations, just like a skilled dancer adapts to changes in music or the floor. The wheels and motors move the robot according to the plan, adjusting for bumps and unexpected situations. Remember, just like a perfect tango, autonomous car operation requires perfect timing and harmony between these components. Each plays a unique and vital role, making the seamless navigation of our complex world possible. A few key points which help the above 6 pillars come together seamlessly and are changing the game are as follows. First, the feedback loop. Imagine the tango dancers continuously checking each other's position and adjusting their steps. Similarly, in autonomous systems, there's a constant feedback loop. The robot uses its sensors to check its surroundings and update its internal map, ensuring it adapts to changes like new obstacles or traffic light updates. This continuous learning cycle keeps the dance flowing smoothly. The robot constantly checks its sensors and updates its internal map, ensuring it adapts to changes in the environment. Second is varying architectures. Just like different dance styles require different moves, autonomous robots can have varying architectures depending on their purpose. Some prioritize speed for delivery tasks, while others focus on safety in healthcare settings. Robots designed for collaboration in manufacturing might emphasize communication and data sharing. Each architecture reflects the robot's unique dance style. Third, the advancements. The autonomous Tango isn't static. Just like dance evolves with new techniques, robots are becoming increasingly autonomous. Imagine them learning to handle intricate footwork, complex situations, and even improvising steps, independent decision-making. These advancements are pushing the boundaries of what robots can achieve, paving the way for even more fascinating applications in the future. Forget the map you're used to. Imagine a world where information isn't confined to flat surfaces, but exists in a multidimensional space called featurespace. This concept, crucial in machine learning and data analysis, unlocks hidden patterns and insights that traditional methods miss. The following key components help us better understand the intricacies of mapmaking. First, feature extraction. Imagine extracting key characteristics from objects, like height, width, etc., and a chef carefully picking ingredients. In featurespace, these ingredients become the axes of our new world. Next, the data points mapped as locations. Objects, now described by their unique features, are placed in specific locations within this multidimensional space. Think of it like assigning apartments in a giant multi-floor building, each floor representing a different feature. Third is actually building the map. Imagine algorithms as explorers, traversing this complex space and charting the landscape. They identify clusters, boundaries, and patterns, like neighborhoods in our multi-floor building. Last, one has to visualize the map. This is where the magic happens. We use techniques to project these high-dimensional maps onto lower dimensions, like 2D or 3D, allowing us to visualize the hidden relationships and structures. Think of it like unfolding a crumpled map to see the whole picture. Now you may ask, why is this important? Featurespace helps us understand complex data with many variables. It reveals hidden patterns that might be invisible in traditional analysis. This knowledge is used in various applications, from image recognition to fraud detection. Featurespace mapping is a powerful tool for unlocking the secrets hidden within data. The other application for this is while making movie recommendations, and is discussed in detail in the machine learning module.